Okay, here we are. This is the second lesson devoted to the asymptotic evaluation of integrals. Last time we discussed two main classes of methods, the so-called Laplace method and then second, the evaluation of Fourier integrals by means of the stationary phase method. Today we will generalize the Laplace method to the complex plane, and we will also explain the meaning of the logo of this course, that is this drawing here, because we will address the so-called method of steepest descents, the basic idea of which is very simple. Consider an integral with a large parameter k, which has the same form as a standard Laplace integral. So the integrand is made of a function f of the complex variable z, and then there is an exponential function. In the exponent, you see the large parameter k, and then some further function phi of the complex variable z. C, the integration domain, is a given path or contour in the complex plane of the z variable, and this defines a function of the parameter k that we will indicate with the letter I. Now, the basic idea of the method is to use the analyticity of the integrand, so we may make use of the machinery of analytic functions of one complex variables to deform the integration contour C to a new contour, let us call it C prime, on which the function phi, which is in the exponent of the exponential, has a constant imaginary part. So if you represent this function phi by splitting its real and imaginary parts as u plus jv, where u is the real part and v is the imaginary part, we will consider the locus of points in the complex plane where v, the imaginary part, is equal to some constant. Now, if we let this locus be equal to c prime, we may integrate, we may deform the integration contour from c to c prime, and what we get is a new integral made along c prime, in which, since v is equal to a constant, the exponential with imaginary part v in the exponent can be taken outside of the integral, because that does not vary with the integration variable z. So what remains inside is an exponential function in which in the exponent we have the real part u of our function phi multiplied times k, which is a real parameter. So basically now this is a real exponential. And since this is a real exponential, we may expect to be able to use the same approach for asymptotically evaluating this integral as in the Laplace method that we discussed in the last lesson. This is the main idea. Okay, now this motivates also the name of the method, since we will prove that those paths on which the imaginary part v is constant are also paths for which the variation of the real part is maximal, so it can be in that case we will call of steepest descent, or it may increase, and in that case the path will be a steepest ascent path. In our case, what we will need is the maximal decrease of the real part. And so the asymptotic evaluation of our integral will take the name of the steepest descent method. And usually those steepest descent paths, although not always, but in many cases, those paths go through some point, let us call it z0, for which the first derivative of the function phi is equal to 0. So where the function phi is stationary. Now we will see in a moment that for a stationary point in the real part u, just a moment, let me see if I have to admit someone. Okay, no. Now we will see that a stationary point of the function u is neither a maximum nor a minimum, but rather it is a saddle point. So the method is also known as the saddle point method. So the shape of the saddle point, of a neighborhood of the saddle point, is the one depicted here, in which you can see the point z0 is here at the vertex of two intersecting parabolic contours, in which if you follow one of those contours, the point is a local maximum. But if you follow the other contour, I'm referring to the black lines, in that case, the point is a minimum, and that's the typical behavior in a saddle point, okay? So basically, the function in a neighborhood of this point has not locally a definite sign of its variation, which can be either negative or positive, depending on the direction in which you are moving from the stationary point. Now, let us see all these things a little closer by recalling some properties of analytic functions. We will assume that the function phi of z is an analytic function. This means that the Cauchy-Riemann equations hold for its real and imaginary parts. Remind that the Cauchy-Riemann equations relate the first derivatives of the real and imaginary parts of an analytic function one each other. For example, the derivative with respect to x of the real part u is equal to the derivative with respect to y of the imaginary part v, and vice versa, the derivative with respect to y of the real part u is equal and opposite to the derivative with respect to x of the imaginary part. Now, among the many consequences of those equations, we have in particular the following. If you assume that you are examining some point where phi prime is different from 0, so it's not a stationary point, then if you evaluate the dot product of the gradients of u and v, those are real gradients of real functions. Now this dot product is clearly the product of the components x and y of those two gradients. Those are two-dimensional gradients in the plane. Then you make use here in the next step of the Cauchy-Riemann equations to discover that this dot product is equal to 0. This means that the direction of maximum variation of u is orthogonal to the direction of maximum variation of v, by recalling that the gradient gives us the direction of maximum variation of any function. So the curves where v is constant, for instance, are steepest descent or ascent paths for the real part u. Okay. But in addition to these, the same Cauchy-Riemann equations also tell us that both u and v are harmonic functions. That is because if you evaluate the Laplacian of either one, that is, you sum x and y variables, by again introducing the Cauchy-Riemann equations, you will discover that those Laplacians are identically 0. So we may call those u and v functions harmonic because they are solutions of the Laplace equation in the plane. And we may recall from our second lesson that for harmonic functions, a version of the maximum modulus theorem holds that reads, if u is an harmonic function in some open connected domain d of the plane, then if the absolute value of u at some point x0, y0 is larger or equal to the absolute value of u at any point in this open connected domain, then it results that u is constant in this domain. So we cannot have interior minima nor maxima actually for a harmonic function inside an open connected domain. Equivalently, if you include a boundary to your domain, so you close it, this means that any harmonic function attains its minima or maxima on the boundary of the domain. Okay. But since this is true, then we have that for some interior point of a non-constant harmonic function, all the stationary points must be saddle points, since they cannot be neither maxima nor minima. Okay. So having said that, let us observe a little bit closer what is the behavior of our analytic function in a neighborhood of some saddle point. So let us now assume that the point z0 is a saddle point, and in particular we define a saddle point of order n, capital N, if by letting n, small n, equal to capital N plus 1, the following conditions hold: the derivatives of the function phi of order m up to capital N are identically 0 at the saddle point z0. So we have capital N derivatives which are 0 at that point, whereas the first non-zero derivative is that of order capital N plus 1, that is of order small n. And since it is non-zero, we can write its value as a complex number in polar form with an absolute value a larger than 0 and a phase alpha in the exponent. Now we let the increment z minus z0 be a complex number also represented in polar form, so rho times e to j theta, where rho is the distance between z and z0. And theta gives us the direction in which we are performing the increment in the complex plane. Okay, we can study the local behavior of the function phi in a neighborhood of the saddle point by examining the difference between the function phi at some point z and the function phi at the saddle point z0. Now, this increment by the Taylor expansion of the function can be approximated with the first non-zero term in the Taylor series, which is, by those assumptions in the box, the term of order n, small n. And that term has the form 1 over n factorial times the nth power of z minus z0 times the nth derivative of the function phi evaluated at the saddle point z0. Or, in other terms, given our positions, we have rho to the nth power, e to j and theta, and those two terms come from z minus z0, and then a times the exponential e to j alpha. If we collect the absolute values and the phases together, we have rho to the nth power times a divided by n factorial, and then in a single phase exponential, we have e to j alpha plus n theta. And now we can split this exponential in its real and imaginary part by making use of the Euler formula to have what you can see in the square brackets, the sum of a cosine plus j sine of the argument alpha plus n theta. Okay, now everything except for the imaginary unit is real, and we can study the behavior of the increment of the function in a neighborhood of the saddle point by observing this specific form. In particular, since the direction of steepest descent through the point, the saddle point, are defined by the condition that the imaginary part of the difference phi of z minus phi of z0 is equal to 0, then it follows, by observing the imaginary part, which is represented by a sine function, that we must enforce the condition that this sine function must be equal to 0, because we wish u to decrease away from the saddle point. And since we wish u to decrease away from the saddle point, the real part, that is the cosine function, must be a negative number. Okay. On the other hand, the direction of steepest ascent will be given by the same condition on the sine function, that must be equal to 0, but in this case the cosine function must be positive. In that case, the increment of the function will be positive, and we will have that the saddle point is a local minimum, whereas on the steepest descent path, the saddle point is a local maximum. Okay, as you can see also in the figure here at the bottom right. Now, if you consider the argument of the trigonometric functions, in order to have the sine function be equal to 0, we have that alpha plus n theta must be an integer multiple of pi. And in order to have the cosine less than 0, you will discover that and therefore having the steepest descent directions, you discover that theta must be given by minus alpha divided by n plus an odd integer multiple of pi over n. Whereas the steepest ascent directions are given by, again, minus alpha over n plus now an even multiple of pi over n. Just to give you a simple example, if capital N is equal to 1, this means that the first derivative of the function phi is equal to 0 at the saddle point, but the second derivative is different from 0. So this is the so-called simple saddle point. Okay, let us assume that the second derivative has an argument alpha, which is equal to pi over 2. Then by applying the formulas in the box, you will discover that the direction for the steepest descent paths are given by minus alpha over 2, so minus pi over 4 in this example, plus integer multiples of pi over 2. So those directions are those indicated in green with these dashed green lines that go from the origin, which is assumed to be the saddle point, into the first quadrant along the bisectrix and also into the third quadrant along the bisectrix. Whereas the steepest ascent paths are alternating with the steepest descent directions, and they are given by minus pi over 4 plus an even multiple of pi over 2. So those are the bisectrices of the second and fourth quadrants. And this is the typical situation around a simple saddle point. Okay, we have two directions of steepest ascents, which are alternating with the directions of steepest descent. Okay. Just to give you some more examples, take the function phi to be given by this polynomial of third order, z minus z cubed divided by 3. Okay, let us first of all find if and how many saddle points are there. In order to do that, we will evaluate the first derivative of phi, which is in this case equal to 1 minus z squared, which is again a polynomial, which can be immediately factored as 1 plus z times 1 minus z. So we have two solutions, z equal to plus and z equal to minus 1, at which the first derivative vanishes, and therefore we have saddle points. Let us evaluate the second derivative. At the point 1, the second derivative is equal to minus 2, which can be represented as 2 times e to j pi. So in this case, alpha, the argument of the second derivative, is equal to pi. Whereas the second derivative at minus 1 is equal to plus 2, therefore its argument is 0, and alpha in this case, therefore, is 0. This gives us the directions of steepest descent. For example, for the point 1, where alpha is equal to pi, we have to use this formula, minus alpha over n, which in this case is minus pi divided by 2, to which we have to add an odd multiple, again, of pi over 2. If we do that, we have that the directions are given by the angles 0 and pi. So those two arrows departing from the saddle point at 1, give you the directions of steepest descent from that point. If you examine the other saddle point at minus 1, where alpha is equal to 0 instead, the same formulas give you the angles pi over 2 and 3 pi over 2. So therefore, we have vertical directions for the steepest descent paths. Another example is the second one in this slide, in which the function phi is equal to the hyperbolic sine of z minus z. Let us evaluate the first derivative, which is the hyperbolic cosine of z minus 1. We equate this to 0, to discover that the saddle points are the inverse hyperbolic cosine of 1. Now, as you may recall, the hyperbolic, the inverse hyperbolic cosine is expressed in terms of a logarithm, and therefore it is a multi-valued function in which all the values differ by an integer multiple of j times 2 pi. So in this case, the inverse hyperbolic cosine of 1 is given by 0 plus j to m pi. If we focus on the saddle point at the origin, since for all the other saddle points considerations are exactly the same given the periodicity, where at the origin the second derivative is equal to 0, because the second derivative is equal to the hyperbolic sign of z, which vanishes at the origin. The third derivative is instead given by, again, the hyperbolic cosine, which is equal to 1 at the origin. So in this case, we have a saddle point of second order, since the first non-zero derivative is the derivative of third order. Of course, all the other replicas along the imaginary axis are also second-order saddle points by periodicity. Since in this case, the argument of the first non-zero derivative is equal to 0, that is, alpha is equal to 0, we will apply the formula that gives us the directions of steepest descent as minus 0 divided by 3, in this case, which is again 0, plus an odd multiple of pi over 3. This gives us the directions, which are pi over 3, and then we have 3 pi over 3, which is equal to pi, and 5 pi over 3. So we have 3 steepest descent directions originating from the saddle point, which is a second-order saddle point. Of course, they would alternate with the steepest ascent directions, which are the bisectrices of those 3 angular sectors, but we are not interested in them for the asymptotic evaluation, okay? So, in a nutshell, what is the so-called Laplace method for complex contours? First step, we need to establish that the original contour of our integral can be deformed onto some steepest descent contour, which passes typically through the saddle point, through some saddle point. And this requires that you understand the global geometry of the analytic function you are considering in the complex plane. Usually, the contribution near the saddle point, if any, will give you the dominant asymptotic contribution. Sometimes, however, the contour cannot be deformed onto a curve that passes through a saddle point. And in this case, the dominant contribution will be given by endpoints. For example, if your integration path is starting from some finite point in the complex plane, or from singularities that may be encountered in the process of deforming the contours. And sometimes this deformation process will introduce poles by means of the residue theorem, which may be significant. That is, they may furnish some non-negligible contribution to the evaluation. Sometimes it may even be the dominant contribution. So we need to understand what's happening in terms of the singularities of all the involved functions. Now, let us observe, first of all, what is typically the dominant contribution. That is, let us assume to have a saddle point of order capital N, and let us examine the contribution of a single steepest descent path. So the path in red here that originates from the saddle point and goes all the way down in the fastest possible way along this valley, in this mountain-like representation of the function u. So if z0 is a saddle point of order n-1, small n-1, and we let the function f occurring inside the integral to be locally well represented by some power z minus z0 to the exponent beta minus 1 in the vicinity of the saddle point. That is, we are explicitly assuming that phi of z minus phi of z0 is locally represented by this term in the Taylor series expansion. The first non-zero term is of order n, where the derivative of order small n is given by this form in the polar representation, where alpha is its argument. And furthermore, the function f is asymptotic to some constant f0 times z minus z0 elevated to beta minus 1, where the real part of beta is assumed to be positive. Otherwise, we would not have an integrable function. Okay. Now, given all those assumptions, then it turns out that the dominant contribution to the asymptotic evaluation of the integral is given by this formula, rather complicated looking, but this is not so complicated after all, because as you can see, the first factor is just a bunch of constants. That is, we have f0, then n factorial to the power beta over n, then the exponential function evaluated at j beta theta, divided by n, where theta is, of course, the direction of the steepest descent curve. Then we have the second factor, which also contains a constant, that is the gamma function, evaluated at beta over n. And finally, we have what is the most important part of this formula, that is the dependence on k, which is contained in the numerator through the exponential function e to k phi evaluated at the saddle point. Okay, so this is what remains of the original Laplace exponential that occurred inside the integrand. But in the denominator, we have instead a power of k and also of this constant, the absolute value of the nth derivative of phi at the saddle point. Both multiplied together are elevated to the power beta over n. So as you can see, this exponent beta over n is built from the local behavior of the functions phi and f through the exponents beta that occurs in the local representation of f, and this is the numerator of this fraction, and through n, which is instead related to the order of the saddle point. For a simple saddle point, n would be equal to 2. And so we would typically get fractions in which the denominator is 2, whereas for higher order saddle points, we would have 3, 4, and so on. Let us prove now this formula. Actually, the proof is not so difficult. The point is that since we integrate along the steepest descent path, we will represent the difference between our function phi evaluated at the general point z along the path and the function phi evaluated at the saddle point as a real quantity, since we are moving on, by definition, on a path where this difference must be purely real, and furthermore, it must be negative, since this is a steepest descent path. So we may let this be equal to minus t, so we are now introducing a new integration variable, t, where t is a positive number. Of course, the Jacobian can be evaluated by differentiating, so we have phi prime of z dz is equal to minus dt, okay? And this produces the new integrand in which we have minus f divided by phi prime, where z, of course, is implicitly a function of the new variable t. Then we have now a standard Laplace exponential e to minus kt, and the integration is performed in t from 0 to plus infinity. So this is actually a standard Laplace transform. And finally, the exponential function e to k phi of z0, which is a constant with respect to t, has been taken outside the integral. Now, to evaluate this asymptotically, observe that near the saddle point, the difference phi of z minus phi of z0 is represented asymptotically as the first non-zero term in its Taylor series expansion, so this term here, in which you have the nth power of z minus z0. And this must be equated to minus t in order to perform the required change of variables. So if we now um, apply the power 1 over n to both members of this equality, and we isolate the absolute value of z minus z0 at the left-hand side, what we get is that the absolute value of z minus z0 is equal to t up to 1 over n times n factorial to 1 over n divided by the value of the nth derivative of phi at the saddle point in absolute value elevated to 1 over n again. Okay. So if you focus now on the term in brackets inside the new integral, which contains the ratio between f and phi prime, then you can evaluate this asymptotically in a neighborhood of a saddle point by evaluating the numerator as f0 times z minus z0 up to beta minus 1. This is because one of our assumptions was about the local behavior of the function f, exactly of this kind, as you can see here, whereas the denominator comes from differentiating the function phi once, and so therefore by differentiating its local representation, what you get is 1 divided by n minus 1 factorial times z minus z0 up to n minus 1 times the nth derivative of phi evaluated at z0. Now, by collecting all the pieces together, what you get is this formula here, in which theta must be one of the directions of steepest descent. So theta must be such that theta n plus alpha is an odd integer multiple of phi. If you enforce this in this formula, you will discover the result that was mentioned in the previous slide. So this is the dominant asymptotics for your integral. Okay. But you can do even more. You can go beyond the dominant asymptotics because you can even recover the full asymptotic expansion of the integral. In order to do that, what one must do is to solve for z minus z0 in terms of a full power series in T. So of the kind z minus z0 equal to the infinite summation of Cm times t to the mth power, where m now goes from 0 to infinity. And in order to recover that, you start from the definition of the new integration variable, minus t, which is equal to phi of z minus phi of z0. That is, given the local behavior of the function phi, as the power z minus z0 to the nth power times some analytic function phi hat of z, where phi hat has its Taylor representation, in which you have all the terms from the term 0 up to infinity, since phi hat is analytic close to z0 and it is non-zero at the saddle point. So this is a way to explicitly enforce that we have an nth order 0 for the difference phi of z minus phi of z0. That is, we have a saddle point of the given order. Now, in order to obtain what we need to recursively solve the equation z minus z0 equal to t to 1 over n divided by phi hat of z to 1 over n. That is, we isolate z minus z0 from the above equation, and then we obtain an equation in which z is both at the left-hand side and at the right-hand side, but you can insert this equation inside z at the right-hand side and proceed recursively in order to recover all the powers that you need in the expansion. This may be quite laborious in practice, but it is guaranteed by the implicit function theorem that you can do that. Okay. And sometimes, depending on the specific problems, it may be possible to apply specific techniques to obtain the expansion. One important remark is that since all this is based on the Laplace method, which is in turn based on Watson's lemma, and Watson's lemma is able to provide the full asymptotics, so the full asymptotic series representation of the integral, then the method of steepest descent, or saddle point, inherits from the Watson's lemma this nice property. So by using a purely local information, so we need only to know how the functions behave in the neighborhood of the saddle point, you are able to get the entire asymptotics. An alternative could be to deform the original integration path not to the paths of constant imaginary part v, but rather to the paths of constant real part u. So on those paths, what you get is that the imaginary part v is mostly rapidly varying, and since this is related to the phase of the exponential, what you would have is that you are maximizing the rate of oscillation of your integral. So we are now in a situation close to the case of Fourier integrals rather than Laplace integrals. However, as we commented in the last lesson, the kind of mechanism that determines the decay to zero of a Fourier integral, that is the cancellation due to rapid oscillation of the integrand, is intrinsically a weaker decay mechanism with respect to the real decay of a real exponential as the one that occurs in Laplace integrals. So typically, if you deform to a path where the real part is constant, what you get in general is only the leading term of the asymptotics, but you are not able, through this generalized Fourier integral approach, to derive the entire asymptotic expansion series. Another important aspect, which is related to this consideration, that is from the fact that you only need to know the local behavior of your functions, descends also that the choice of the integration path may be relaxed, since it is in practice sometimes difficult to find the exact steepest descent path. But actually what you need is not the exact steepest descent path. It is sufficient that you choose some integration path that locally, again, so in the close vicinity of, say, the saddle point, behaves as the steepest descent path. For example, a contour C1 that coincides with the steepest descent contour for some finite length near the critical point, for example, near the saddle point or near the end point or singularities and so on, but that then continues merely as a descent contour, is said to be asymptotically equivalent to the actual steepest descent path. So what you need is to match the contour that you are using with the actual steepest descent contour. But aside from this neighborhood, your contour can do whatever you like as long as it continues to be a descent contour. So that's important, because otherwise you would get contributions that are not negligible. But as long as this is a descent contours, the errors that you introduce by not using exactly the steepest descent path are asymptotically negligible, because they are exponentially small with respect to all the powers that will occur in your asymptotic expansions, and therefore they are terms beyond all orders. Okay. And we will give the first work as example before doing our break. That is, we will illustrate how to find the complete asymptotic expansion of the integral I of k given by this finite integration from 0 to 1, the integral being the product of the logarithm of t, the integration variable, and the Fourier exponential e to j kt. Of course, the asymptotics is in the limit of a large k parameter. Now, since we have a Fourier exponential, our first idea could be to try with the stationary phase method. However, the phase being given by the function phi of t equal to t, if you differentiate the phase in order to find the stationary points, and I recall that the stationary points are those where this first derivative is equal to 0, you will discover in this case that the first derivative is never 0, since it is equal to the constant 1. So we have no stationary phase points. Now you could also integrate by parts, given the finite rate. Derivative of the logarithm 1 over t is not integrable close to one of the endpoints, that is close to the origin. So since this real integral cannot be evaluated easily with real techniques, a good idea is to go into a complex plane, so to consider it as an integral in a complex plane. So instead of using the real variable t, we will introduce the complex variable z, where z is equal to x plus jy. Now the function phi in the exponential function is given by jz. We now incorporate the imaginary unit j inside phi, since we are dealing with a complex exponential. That is it is equal to jx minus y. Its first derivative in this case is equal to j, so it's never equal to 0, and so we don't have any saddle point in this function. However, it is still possible to find the steepest descent or ascent paths, because by definition those are the paths where the imaginary part of phi is a constant. So in this case, given function of phi, its imaginary part is jx. So those paths are the paths where x is constant. So they are vertical lines in the complex plane. In particular, observe now the real part, which is given by minus y. If we wish a steepest descent path, we need a real part that decays. So since the real part is given by minus y, we will have a decay when y is positive, whereas we will have an increase if y is negative. So the steepest descent path is at the half line, which is vertical, that starts from the real axis and goes upwards, whereas the steepest ascent path is again a vertical half line that originates from the real axis but now go downwards. Okay, so we will integrate along the SDPs. However, note that the imaginary part at the right-hand point, 0, is different from the imaginary part at the at the left-hand point, 0, is different from the imaginary part of phi at the right-hand point. So those 2 points do not belong to the same path of steepest descent. And in fact, the steepest descent path from the origin goes all the way vertically through the positive y-axis, whereas the steepest descent path from 1 goes all the way vertically from the point 1, and those are 2 parallel half lines. So in this case, what we can do is to try with the Cauchy theorem to connect the points 0 and 1 in the complex plane, but instead of going through the real axis, as in the original integral, we will go through this deformed contour that is made from a vertical segment, C1, a horizontal segment, C2, at some height, R, above the origin, and then we will come finally to 1 through this vertical C3 path. Now, since our integrand is analytic inside this rectangle, Cauchy theorem allows us to say that the original integral, evaluated from 0 to 1 along the real axis, must be equal to the integral evaluated in the path formed by C1, C2, and C3. So those are equivalent. And let us split the contributions of those 3 edges of the rectangle. The first edge, C1, goes vertically. It can be parameterized with R, a real variable that goes from 0 to capital R. And z is equal to jr, since we are going in the vertical direction of the imaginary axis. So you can see that this j pops out of the integral, we have the logarithm of JR, and the exponential becomes real, e2 minus KR, as it must, since we are moving on a steepest descent path. We integrate from 0 to capital R. Then we have C2, the upper horizontal edge, that goes from, in this case, it is parameterized by x, so we will let z be equal to x plus j capital R. And x goes from 0 to 1. So this is what you get inside the integral. And finally, we go along C3. So since we are moving downwards, we will introduce a minus sign in front of the integral that is evaluated from 0 to capital R. And in this case, the integration variable z will be given by 1 plus jr. Again, we see the occurrence of the real exponential as we are moving again on a steepest descent path. And we have been able to take outside of the integral the constants j and e to jk. Now, the trick in order to achieve the evaluation is to get rid of the horizontal, the contribution of the horizontal term, C2, by letting capital R go to infinity. Well, actually, infinity is the place where those two parallel half-lines meet. Now, if you let capital R goes to infinity, observe the second integral, these intermediate ones, that is the contribution of C2. What you have is that at infinity, the exponential function goes to 0, because as you can see here, you have e to jk times jr, which gives you e2 minus kr, and that goes exponentially to 0 at infinity. And therefore, it wins over the logarithm. And since anything is integrable, it is possible to switch the limit and the integration, and to conclude that in the limit, we have the integral of 0, that is, we have 0. So the contribution is negligible when r tends to infinity. So we remain with the first and third integrals that now can be evaluated both from 0 to plus infinity. Okay, so our task will be that of asymptotically evaluating those two integrals. And let us start with the left one, in which we have a logarithm and an exponential, a Laplace exponential. Now, in the first integral, it's immediate, the evaluation. We just need to change variables. So by letting s be equal to kr, what we get in the first integral is what you can see here, j over k, which comes from the change of variables. Then we have the integral of the logarithm of j over k plus the logarithm of s. This is all multiplied by e2 minus s, and it is integrated with respect to s. This gives you a term that depends on k, like the ratio of the logarithm and of k itself. And then we have this constant j gamma plus pi over 2 divided by k, where gamma is by definition minus the integral from 0 to infinity of the logarithm times the exponential e2 minus s. This is a standard representation of an important mathematical constant, which is given with a few decimal places here, 0.577216 and so on, the so-called Euler-Mascheroni constant, which is an irrational constant. Well, actually, we do not even know if it is rational or irrational. It is rather mysterious. As long as we know from calculating its decimal places, we have not found a period so far. So it seems irrational, but we don't have a proof. Okay, given this, we have achieved the asymptotic evaluation of the first integral, whereas the second integral can be evaluated in a standard way by using Watson's lemma, because we can expand the logarithm of 1 plus jr, which occurs here in the second integral and multiplies the Laplace exponential, through its Taylor series, which converges inside a circle having its center at 1 and radius 1, as you know, because the logarithm has a branch point at the origin. So the radius of convergence of this series is limited by the fact that we have a branch point at the origin. But we don't care about the radius of convergence because, as you know, the asymptotics comes from the vicinity of the critical point, in this case, the point 1. So we just need to know all the terms of this series, insert it into the integral, and then integrate term by term, which is the, 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 um, the idea behind Watson's lemma. And what you get is this infinite summation here, you can see. So finally, you can see in the green box, by putting all the pieces together, the complete asymptotic expansion, which is made in this case not only from inverse powers of the large parameter k, but also from this term here, that is the ratio of the logarithm and the first power of k. Okay, so this is the dominant asymptotics. And then there are all the higher order terms. Okay, I think that this is the right moment for making a break. So let's make a 50 minutes break and see at 5 minutes after 11. See you later. Okay, here we are. After this first worked example, we will go on considering a second worked example. This concerns the so-called Hankel function, which is, of course, an important function in the study of wave phenomena when you consider cylindrical coordinates. The task is to find the complete asymptotic expansion of the Hankel function of order Ni, here in the subscript, and of the first kind in the superscript of K, which can be represented in many alternative ways. In particular, we will consider an integral representation of this function, which reads 1 over pi, the integral along the path C that you can see here in the inset figure. There is a line that goes from infinity in the vertical direction inside the strip of the second quadrant, whose real part goes from minus pi to 0. And this is a rather arbitrary path as long as it goes to infinity downwards in the strip of the fourth quadrant with real part between 0 and pi. Okay, the possibility of changing the shape, the exact shape of this contour comes from the fact that we are integrating entire functions. In particular, we have inside the integral the first exponential function e to jk cosine of z, and the second exponential function is e to j ni times z minus pi over 2. We are interested in evaluating this asymptotically in the limit of k going to infinity. So k is our large parameter. Let us try to apply the method of steepest descent, or the saddle point method, by first ascertaining what is the function phi. You can read it as what multiplies the large parameter k in this exponential function, and therefore phi of z is given by j times the cosine of z. To find the saddle points, let us find the first derivative, phi prime, which is given by minus j sine of z. And therefore, all the points that make the sine function 0 will be saddle points of first order. And in particular, those points are the origin and any integer multiple of 2 pi by the periodicity of the sine function. Since we are in the strip between minus pi and plus pi, we will address the origin as our saddle point. Okay. This is a simple saddle point because the second derivative is different from 0, and in particular, the second derivative would be equal to minus j cosine of z, that at the origin is given by the constant minus j. In polar form, minus j can be written as e2 minus j pi over 2, so the parameter alpha, that is the argument of the second derivative at the saddle point, is given by minus pi over 2. With this information, we are now able to find out what are the directions of the steepest descent lines that originate from the origin by employing the general formula minus alpha divided by n, where n is 1 plus the order of the saddle point. In this case, the order is 1, so the denominator is 2. So minus alpha divided by 2 plus an odd integer multiple of pi over 2. And this gives us the two directions, 3 pi over 4 and 7 pi over 4. That is, we need to move along the bisectrices of the second and fourth quadrants. Okay? Now, if you note that the integral along C can be written as the integrand along C2 minus the integrand along C1, where C2 goes into the fourth quadrant, as you can see here, whereas C1 goes into the second quadrant. Then for both C1 and C2, we can employ the general formula that we derived before, that is repeated here in its general term, and we will in particular enforce this formula for the specific case we are considering by letting, for example, theta equal to 3 pi over 4 for C1, or 7 pi over 4 for C2. And the saddle point Z0 is at the origin, so Z0 is equal to 0. It's a first order saddle point, so n is equal to 2. The value of the function phi at the origin is equal to j, as we already found, whereas the second derivative is given by minus j. The function that multiplies the exponential is an exponential function, so it's regular inside in a neighborhood of the origin where it is equal to 1. But what we need is to know that close to the origin, it goes to a constant. So if you remind the assumptions, let me back here. The assumption on the function f is that it is locally represented as f0 times z minus z0 up to beta minus 1. So if the function f is locally a constant, this means that the exponent must be equal to 0, that is beta must be equal to 1. And so in our example, we let beta equal to 1, and the constant f0 is just the function e to j z minus pi over 2, including also the factor 1 over pi that was outside the integral. All these must be evaluated when z is equal to 0, because we are at the saddle point. This gives us 1 over pi times e2 minus j ni pi over 2, which is what is written here. Okay, so once you have all those numbers, you insert them in the formula, and you discover that the Hankel function of order 1 is given to the dominant asymptotic order by the square root of 2 over pi k times the exponential with the purely imaginary exponent e to j k minus ni pi over 2 minus pi over 4. Which is important to know because this tells us that asymptotically those Hankel functions behave as weighted exponentials with a purely imaginary exponent, where the weight is the spreading factor typical of cylindrical waves, typical of the spreading in amplitude of cylindrical waves. I'm referring now to the case when the argument of the Hankel function is given by some constant times the radial distance from the z-axis in a cylindrical coordinate system. Okay, so here we have that asymptotically the wave behaves like a plane wave whose amplitude is weighted by this factor here. Now, similar considerations could also be done for the other Hankel function, that of order 2, in which we would find exactly the same formula but with a minus sign in the exponent. So one of those two functions represent outgoing waves, the other one represents ingoing waves. Which one of the two represents the outgoing or the ingoing? That depends on the convention on time that you have chosen. So if, as is typical in engineering, you choose an E2 plus j omega t convention, then it's this first order Hankel function represent inward waves. Physicists use typically the opposite convention in time, so they have E2 minus I omega t, and therefore for them the Hankel function of first type is an outward wave. Okay, this was just to place this in the context of waves. Now, let us examine a bit more closely the actual shape of the steepest descent contour. This can be done by enforcing that imaginary part of phi be equal to the imaginary part of phi evaluated at the saddle point, and this gives you the explicit equation for the steepest descent contour, that is the cosine of x times the hyperbolic cosine of y must be equal to 1. This is in implicit form the equation of a curve in the xy plane that can be studied in the neighborhood of its point at the origin by expanding both the cosine and the hyperbolic cosine through their Taylor series, having as initial point the origin. If you do that, you will discover that the function at the left-hand side, so the product of the cosine and the hyperbolic cosine, assumes the form of the product of two linear terms, y plus x and y minus x, which are respectively the locally tangent lines to the steepest descent paths actually, and the steepest ascent paths. Okay. In particular, when you equate y plus x to 0, you have the equation of the bisectrix of the second and fourth quadrants, that is the tangent line to the steepest descent path that you can see is represented here with the arrows going in the direction of descent from the origin, because the origin is the local maximum of the real part of the exponent. When y in absolute value goes to infinity, the hyperbolic cosine goes to infinity, and therefore to be still on the path, we must have that the cosine of x goes to 0. This means that x must go either to minus pi over 2 or to plus pi over 2, and this is actually what happens here. In the upper leg of the path, we go to minus pi over 2 asymptotically in x, whereas the downward leg tends in x to pi over 2. Okay. Note that the original integral converges only if the real part of phi is negative, because otherwise the exponential function would diverge. And this gives us that the region of convergence of the integral are the two half strips in the second and fourth quadrants. In the second quadrant, x must be between minus pi and 0. Here there is a missing minus in front of this pi. I don't know why. Whereas in the fourth quadrant, when y goes to minus infinity, so again there is a missing minus. This minus sign has some problems with my editor. And we are in the half strip where x is between 0 and pi. Okay, so the regions of convergence contain, fortunately, of course, our steepest descent path. And therefore, we may deform our original contour, which was this one, to the steepest descent path. That was the first thing to check. Otherwise, the method of steepest descent cannot be applied. Okay, having said that, we have discovered the dominant asymptotics. We can go beyond by expanding through the steepest descent transformation z in terms of the new integration variable we mentioned before. If you do that in this particular case, you have that j cosine z minus 1 must be equal to minus t. And if you expand the cosine function through its Taylor series, that converges everywhere in the complex plane, by the way, you have that this infinite summation on the left-hand side of this equation is equal to e2 minus j pi over 2 times t. Now, this gives us t in terms of an infinite summation of powers in z. What we need, however, is the opposite. So we would be able to express z as an infinite summation of powers of t. So what you can do from this equation is that you can take the square root after you isolate the first term in z, so z squared divided by 2. If you do that, you have that z is equal to the square root of 2 times e2 minus j pi over 4 times the square root of t. And then we have these brackets that contains all the higher order terms in z. Now, you can use this formula iteratively by plugging into z at right-hand side exactly what you see in the entire right-hand side. So if you do that for all the terms, what you get is, at the end, a series in which z is not present anymore at the right-hand side, and you only have powers of t. In particular, the first power is t to 1/2, then we have t to 3/2, and so on. This is what we need, because we now can use these expansion to evaluate our Hankel function. So we have our integration along the steepest descent contour of the exponentials. In particular, we can take outside all the constant terms from the integral, so that inside the integral what remains is just the real Laplace exponential e to minus kt. And then we have the exponential that contains the order ni of the Hankel function times z as a function of t. This exponential can be in turn represented through its Taylor series, which converges again in the entire complex plane. And finally, with much work, we can insert the expression of z as an infinite summation of powers of t inside each of the infinite terms of this infinite summation in z, in which I guess there is also a missing exponent 2 here, by the way. And also inside the Jacobian, there is the derivative of z with respect to t. If you do that, I would not advise you to do that, but if you are forced by life to do that, at the end, you will discover that your integrand is given by an infinite series, of course, of terms containing powers of t, which you can now integrate term by term. And this is why the gamma functions appear, because now what you have to integrate is the product of the Laplace exponential times different powers of t, which is the integrand that defines the gamma functions. In doing that, you will need to change variables, and from this change of variable, the various powers of k will originate in the denominator. So in the end, you get an asymptotic series in inverse powers of k, the dominant term of which is the one in which the power is 1/2. And that is exactly the dominant term that we evaluated with the formula that we used in the first part of this discussion. Now, inside the brackets, you also can see all the higher order terms. Okay? And this is done, of course, for a single steepest descent path. You do that for both, and then you add the two contributions to have the final result. As you can see, everything is quite complicated from an algebraic point of view, but it can be done in principle. There is, however, fortunately, an alternative approach which is somewhat quicker and is probably also more common, at least in the electromagnetic literature, which is based on a different change of variables. In particular, it is based on introducing a suitable polynomial tau of the new variable s, in which the function phi of z is equated to this polynomial in terms of the new variable s, and this determines the actual change of variables, that is the link between the old and new integration variables. So if you start with the same integral as before, by changing variables, what you get is a new integral in s, in which the new integration path is p prime. The function g of s contains the original function f and the Jacobian, so the derivative of z with respect to s, which can be evaluated in turn by means of the implicit function theorem as the ratio between the first derivative tau prime of s and the first derivative phi prime of z. Okay, this is the function g. And finally, we have the Laplace exponential, in which now we have a polynomial in the exponent. Now, with this mapping, with this change of variables, we have a mapping between the old complex plane z and the new complex plane s, in which the vicinity of the old saddle point zs becomes the vicinity of the origin 0 in the complex s plane. So we have our integral along p prime. I think that the figure is not so clear, but however, p prime would be this path here, just to as an example. This should be deformed to become the steepest descent path, let us call it P, that goes through the origin or close to the origin. In doing this deformation, however, we must be careful because there could be singularities occurring around. In particular, if you have poles, like you can see here, you have to use the residue theorem to um, find out their contribution. Whereas if you have branch points, that is tougher, because in that case you also have a branch cut, this wiggly line. And since you cannot deform the integration path by intersecting a branch cut, what you need to do is to circumvent the branch cut by integrating along the two rims of the branch cut. So what you get is an additional contribution, that is the integral along this folded integration contour that goes around the branch cut. So our original integral is given by the contribution of the steepest descent contour, P, plus the integral of these small circles around the poles, which are equivalent to the residue contributions, and finally the contribution of the branch cuts, if any, or better, of the integrals around the branch cuts. This is the general situation. Let us see how this works. For example, let us assume a simple situation in which the function g is regular close to the origin, which is our saddle point. If g is regular, we may approximate the function g with its value at the origin. So this is a constant which can be taken outside the integral. And what remains inside the integral is this blue integral here, is called in the literature a comparison integral. Why? Well, because take in mind that the transformation of variables in which tau of s is equated to phi of z is chosen so that the real part of tau decreases most rapidly from the origin, so that the saddle point of this tau function is at the origin or is close to the origin. And furthermore, the derivative of the mapping should be finite near the origin. That is because we are assuming that the function g is regular in the vicinity of the origin. And I remind you that the function g, by definition, contains the mapping derivative dz over ds. So this must be regular. Now, these requirements can be met if the derivative tau prime has the same order of 0 at the saddle point as the original function phi has at the original saddle point in the z-plane. And again, this is because the derivative of the mapping is given by this ratio, so we wish that the numerator and the denominator have the same order of 0 in the vicinity of the respective saddle points. Now, you can choose any function tau as you like, as long as those requirements are met. And typically, the simplest function tau is the one that is chosen to build the so-called comparison integral that is then evaluated analytically. Let us see how this works by examining for the second time the worked example about the Hankel function. So again, we have the function phi that is equal to j times the cosine of z. So with the same steps as before, we discovered that the origin is a simple saddle point. Now, here the alternative method departs from the previous one. What we let is that what we do is that we let the function phi, that is j cosine of z, be equal to its value at the origin, so j, minus s squared, so to obtain a second order polynomial tau in S. Why second order? Well, because since we have a first order saddle point, we wish that also the function tau has a first order 0 at the origin, and since tau prime is given by minus 2s, we will see that actually the origin is a simple 0 for the function tau. And why is this useful? Well, because if we now calculate the mapping derivative, dz over ds, and by means of the implicit function theorem as the ratio between tau prime and phi prime, this is of course an indeterminate form, because both the numerator and the denominator go to 0 when we approach the saddle points in the respective complex planes. However, we may employ the L'Hopital rule, so we may differentiate both the numerator and the denominator. In the numerator, what we get is tau the second derivative of tau, which must be evaluated at the origin. In the denominator, we need an additional step. We first differentiate with respect to z, so we get the second derivative of phi with respect to z, but take in mind that now z is an implicit function of s, so we must include also the derivative of z with respect to s and evaluate it at the origin. So what you find is that if you evaluate these at the origin, what you have in the left-hand side is also present at the right-hand side in the denominator. So you can move that part of the denominator at the left-hand side, and what you get is that the square of the mapping derivative at the origin is given by the second derivative of tau at the origin divided by the second derivative of phi at the saddle point. And finally, if you take the square root, you are able to evaluate the mapping derivative at the origin as the square root of this ratio of second derivatives. Those second derivatives were calculated in the previous slide, so they are respectively equal to -2 and -j. So in the end, we get this complex number that is the square root of 2 times the exponential e to j minus pi over 4 plus integral multiples of pi, in which if the integral multiple is even, what you get is the direction of the steepest descent path. Now, why did we calculate this? Well, because the function g contains the mapping derivative by definition. So if you wish to evaluate that function at the origin, you need to know the value of the mapping derivative at the origin, and now we know it. We are able to perform this calculation, and we discovered that we have this nice purple constant here, 1 over pi, times the exponential e to minus j in e pi over 2 times the square root of 2, the exponential of minus j pi over 4. Armed with this number, with this complex number, look now how to use it in the evaluation, in the asymptotic evaluation of the Hankel function, whose definition is repeated here. This is the original integral in z, which has been replaced by a new integral in s, where now the integration limits goes from minus infinity to plus infinity as we are running through the steepest descent contour. We now replace the function g of s with its value at the origin, that is at the saddle point in the s-plane. And this is highlighted in purple here, whereas the remaining integral is highlighted in blue. Now, the purple constant has been evaluated in the previous slide, and it is repeated here, whereas the blue integral is actually the integral of the exponential e to k times j minus s squared, which is our function tau, a second-order polynomial. So you can take outside of the integral also the term e to jk, that is in blue, because it comes from the integration. And what remains now is a canonical integral, which is the Gauss integral, and that's equal by simple change of variables to the square root of pi over k. So putting all pieces together, again, you recover the dominant asymptotics of the Hankel function as we, exactly in the same form, of course, as we derived in the previous treatment of this example. However, with this alternative approach, it is also quite simple to obtain also the higher order terms. What you need to do is not limit yourself to replacing the function g with its value at the origin, but as representing the function g through its Taylor series expansion in a neighborhood of the origin. This Taylor series will have in general a finite radius of convergence. However, as we said many times, what we need is to know the local behavior of the function. So we don't care about the fact that the radius of convergence is finite. We just integrate term by term this series, which is, by the way, not legitimate mathematically, because since the radius of convergence is finite, you could not actually switch the integration and the infinite summation. So the step is not an exact step, but it is asymptotically correct. So it gives you the right asymptotic series, exactly because what we need is the local behavior of the function to get the asymptotics. If you do this switching, you now have the infinite summation in black outside, and what remains inside the general term is an integral that now involves the product of the exponential in blue times the monomials s to the nth power. So by taking outside the constant, the blue constant e to jk, in the end we get an infinite summation in which what we need to evaluate are those standard integrals whose evaluation is a standard exercise in calculus. You will discover as an exercise that if n is odd, those integrals are equal to 0, and that is immediate because then the integrand is an odd function of s. Whereas if n is even, they can be evaluated in terms of the function square root of pi over k, which is the dominant term that occurs when n is equal to 0, by successively differentiating this term. So introducing monomials inside the integral is equivalent to differentiating the result of the integral. So if you perform those differentiations, you will find all the next powers of k in the asymptotic expansion, in the complete asymptotic expansion of the Hankel function. Now, as we already said, in order to have a regular function g, the derivative tau prime should have the same order of 0 as the original phi prime has in the z-plane. However, it may occur in practical cases that the function f has singularities close to the saddle point, and this translates into the function g having singularities near the saddle point at the origin. Now, in order to treat those cases, those singularities must be isolated, possibly in the simplest form, and this gives rise to new classes of comparison integrals. So instead of having Gaussian integrals, we will have some different kind of comparison integral. And we will finish this lesson by illustrating an overview of some important cases that may occur in practice. For example, let us start with the simplest case. That is the case in which the function f is actually regular, close to the saddle point, and the saddle point has a general order m. Now, when you have a situation like this, which is the simplest case, what you need to do is to equate the original function phi in the exponent of the Laplace exponential to tau, which is now a polynomial of order m plus 1. So you write this polynomial as the value of the function phi at the saddle point minus the monomial s to m plus 1, so that the saddle point zs is mapped into the saddle point at the origin. Now, with this change of variables, the evaluation, at least for the dominant asymptotics, proceeds as we have already seen. So we replace the function g with its constant value at the origin, which can be taken outside of the integral. The exponential function splits into a constant term, which is also taken outside of the integral, e to k phi evaluated at zs. And what remains inside the integral is in blue here, an integral in s that goes from 0 to plus infinity, and the integrand is e2 minus k s to the power m plus 1. This is a canonical integral that can be evaluated analytically, and the result is an inverse power of k. In addition, there are some constants, as you can see, 1 divided by m plus 1, and the gamma function evaluated at 1 divided by m plus 1. But the interesting part is the dependence on k, which is the inverse power of k, the power being 1 divided by m plus 1. So if you have a saddle point of order 1, a simple saddle point, what you get is 1 over k to 1/2. If you have a second order saddle point, you get 1 divided by k to 1/3, and so on. This is the standard situation. However, it may occur a second case in which you have two saddle points at z1 and z2, both simple, and those saddle points are arbitrarily close to each other. And function f is again regular in a neighborhood of both saddle points. Now, if you are in a situation like this, your mapping should be such that you recover a pair of saddle in the S-plane. And the simplest way to do that is to equate the function phi to a third-order polynomial, in which, as you can see, there is a constant, a0, plus a linear term, sigma s, where sigma is a constant, and then there is minus s cubed divided by 3. If you use this form for tau, then those two saddle points are mapped into a pair of saddle points in the complex S-plane that are on the origin at plus or minus the square root of sigma, if sigma is a real number, or are generally two complex numbers that are opposite with respect to the origin. Now, sigma is a parameter that can be arbitrarily small in absolute value, so those two saddle points may be arbitrarily close to the origin, so they tend to coalesce when sigma goes to 0. Now, in this situation, you proceed again by approximating the function g through its constant value at the origin, which is taken outside the integral. And inside the integral, what remains by a change of variables becomes a new canonical integral, this one in red here, in which the parameter z, zeta, Greek z, is equal to k to 2 over 3 times sigma. This canonical integral defines a complex function that is a special function that is known as the Airy function. This comes from the name of the astronomer Airy that we already encountered, and this is the function that occurs, for example, in the mathematical treatment of rainbows, and it's also known, therefore, as the rainbow function, and the integral in red is also known as the rainbow integral. So anyway, this is a function that is tabulated. It is very well known. So when this case occurs, as you can see, you have this term here, 1 over k to 1/3. But in addition to that, you also have a special function, the Airy function, evaluated at this parameter Greek z. The third case is that of three saddle points arbitrarily close to each other. And as you can imagine, in this case, what you need is a fourth-order polynomial in order to recover three saddle points in the complex S-plane, in particular with this choice of the fourth-order polynomial that you can see in the box. In the S-plane, you will find these three saddle points. One is at minus j square root of a, the other is at the symmetrical point plus j square root of a, and the third one is exactly at the origin. When a goes to 0, those three saddle points coalesce at the origin. If you now insert these inside your integral, what you will find is another different kind of comparison integral, this one, which defines a different kind of special function that is known as the parabolic cylinder function, that is indicated as d, having order minus 1 over 2 and argument a times the square root of 2k. In addition to this, you also have the explicit term 1 over 2k to 1/4 outside here in black. Okay, and one could go on. Of course, the higher number of saddle points are occur rarely in practice, but it may happen that sometimes a huge number of saddle points coalesce into the same location of the complex plane. So you should be prepared to evaluating different kinds of comparison integrals. A fourth very important case is that in which you have just one saddle point, as at the beginning. Function f now is not regular close to the saddle point, but rather it has a simple pole, or also a multiple pole actually, at some location zp, which is however arbitrarily close to the saddle point. So we are now evaluating an integral in which there is a pole that can go close to the saddle point, as close as we wish. Now, the mapping between z and s is given in the standard way as a second order polynomial, as in the green box on the left. However, what we need to consider carefully now is the function g, because inside the function g we will have our offending pole that must be isolated. That is, we must write the function g. Well, we must. One possibility is to isolate it in this way by writing the function g as the sum of two terms. One contains the pole at some point b in the s-plane, which is the mapping of the point zp in the z-plane. And the remaining addend that we are calling here t of s is a function that is now regular in the vicinity of the origin. So if you do this, this is called the additive treatment of pole singularities, what you get is a splitting of your original integral into two integrals. The blue one is the one that contains the regular function t, and that can be treated in the standard way. So this gives rise to a constant t of 0 outside the integral times the same canonical integral that we found in case number 1. Okay, so basically an exponential function of k times the inverse power of k to 1/2. But there is the additional term that originates from the singular term here, the one containing the pole, and that is the red integral at the bottom that defines a new canonical integral, and that is expressible, as we will see in the last two lessons of this course, in terms of an additional special function that is in this case the error function. Also, equivalently, it can be expressed in terms of Fresnel integrals. Okay, this concludes the lesson for today. What I've said is taken mostly from the book by Ablowitz and Focas. However, as concerns the alternative approach to the method of steepest descents that I've illustrated in the second part of the lesson, what I've used is the beautiful fourth chapter of this fundamental book by Felsen and Markowitz, Radiation and Scattering of Waves, which is a sort of Bible of these kind of things. It's a very difficult book to read because anything is strictly related to many places in the book. So basically you have to read the entire book if you wish to have a clear view of the situation. However, fortunately, the fourth chapter, which is devoted to the asymptotic evaluation of integrals, is self-contained, so you can extract it and study it if you need it. Okay, that's all for today. So thank you for your attention. I will send these slides to both Fabrizio and Henry, because I think that the problem with the website has not been solved.
Yes, thank you very much.
Oh, no problem.
Thank you.
And okay, so we are done. Let's see on next Tuesday for an application of all these techniques to practical cases. Thank you and have a good day.
Thank you, Professor.
You too. Bye bye.
Grazie mille, buona giornata.
Arrivederci a
Bye, bye.
tutti.
Paolo,
Bye-bye.